You're here because you want to master separation techniques with a University of Cambridge graduate. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. Now let's move on to separation techniques. And separation techniques is actually one of the more important chapters in chemistry, where you actually need to know exactly what is the different procedures and techniques you should use whenever you're given a mixture or whenever you're given a different combination of substances, right? So if I were to separate a solid from a liquid, right? Okay, you would usually think about these few techniques in order. So priority number one, I'll actually think about filtration first because it's very easy to do filtration itself. Right? How does filtration work? You pour the mixture into a filter funnel that is lined with filter paper, and then you collect the filtrate in a conical flask. And then you actually collect the residue and dry it on a piece of filter paper. So if there was a diagram right here, this would clearly illustrate it. Right? So this is where your mixture is actually poured onto the filter funnel that is lined with filter paper. Alright? And all the filtrate, okay, which is the stuff that is leaking down to the bottom, okay, will be collected in a beaker below, okay, and your insoluble solids, alright, is called a residue, and it will actually be caught by the filter paper. So that's exactly how you can separate a solid from a liquid. Another way is to do evaporation to dryness. Okay, so you can heat the solution in an evaporating dish and then remove all the liquid through evaporation. Okay, you're basically boiling it all away or evaporating it all away, right? And you're leaving whatever impurities or solids that were inside the liquid itself. So for example, over here, this is exactly how your evaporation to dryness works. You usually use a crucible, okay, and a Bunsen burner, and you will heat all the liquid out. So do take note that this only works if we do not need to collect the liquid. Okay, because the liquid is just going to evaporate away. So if we have no care for it, then okay. So that's priority number two. We will think about evaporation to dryness. And priority number three, okay, the last method, right, which is also used, you can use crystallization as well. So this is where you can dissolve the solid in water, then you filter to remove any insoluble impurities and collect the filtrate, right? And once that's done, you have a pure solid that's actually dissolved in the solution. Next, you can crystallize it, right? So you usually heat the solution to saturation, leave it to cool to crystallize, okay? And then once the crystals are formed, you can filter to collect the crystals as the residue, okay? And then you wash it with little cold distilled water, and then you dry between a few sheets of filter paper. So this is also another method which you can use as well. And typically, it will look something like this, where you can have a beaker, or you can actually have a little evaporating dish with the solution itself. You heat it to saturations and then you let it cool for crystals to form, then you filter it. We have to also think about how we can separate solids from solids, alright, because sometimes we do have a mixture of solids itself. One way is that we can use a suitable solvent. So if we find that one solid is actually soluble and the other one is not really soluble in another solvent, right, we can use this to separate. So first we can add the solvent, we dissolve the soluble solid, and then we filter. Alright, so when we filter, right, what's going to happen, okay, is that the residue found here, okay, will be the insoluble solid, right, that's not really dissolved in the solvent itself. Okay, and what leaks down into the beaker over here, okay, this is the filtrate. Okay, and this filtrate, okay, has the soluble solid inside the solvent. Alright, so the solid is actually dissolved inside the solvent and it leaks down. And then what's going to happen after that, you've actually successfully separated out the insoluble solid. Okay, we call it solid A for example, and then solid B is dissolved and leaked into the filtrate. And what's left is you can do evaporation to dryness afterwards to collect your solid from the solvent itself. Understand? Now next, okay, we have sublimation as well. This is another technique that we can use. So we usually use this when we find that the solids have, okay, very different boiling points. Okay, So how we do sublimation is we actually heat the mixture, and then one of the solids that reaches its boiling point will actually sublime, so it will become a gas. Okay, and how we collect that gas that turns into a solid is we can deposit it on some cooler surface like a filter funnel, okay, and then you will stop the heating afterwards once you collect the other solid. So deposition is the opposite of sublimation, right? When you collect the gas, okay, the gas will cool down, okay, and become back a solid itself. Now, some schools might teach that if you want to separate a solid from another solid, okay, you can also use a magnet as well. Okay, if there's any magnetically attractable substances, you kind of learn this from your primary school as well. What's new is how you are actually going to separate a liquid from a solution, right? Or basically, how you're going to separate miscible liquids. Right, and how you separate them is actually based on the difference in boiling point. So what you can use is actually a simple distillation. How this works is it pretty much follows this setup here. I'll be mainly using this setup to help explain the processes inside the distillation. So this is our typical distillation setup. Here we have a round bottom flask, right, with our mixture of liquids over here, and we have a Bunsen burner for heating, right? And since we are going to separate them based on their difference in boiling point, we're going to have to boil them, okay, but in sequence. So for example, right, if we have liquid A and liquid B, right, at different boiling points, for example, let's say this one is at 50 degrees Celsius and this is at 100 degrees Celsius for a boiling point. What's going to happen is that as you heat it, right, there's going to be vapors, okay, because you are boiling and you're also evaporating the liquid, and the vapors are just going to come up all the way, okay, to the intersection point. Okay, the purpose of the thermometer is actually to measure, okay, the temperature of the fumes. Alright, and the whole purpose of this, right, is actually to just identify the gases being condensed later on. For example, if you're going to boil it, okay, and the vapors are going to rise, okay, the vapors are actually slowly increasing in temperature. Okay, remember, right, your liquid doesn't have to boil to become a gas, it can actually evaporate. Okay, so maybe at 40 degrees Celsius, you're still collecting gases of both liquids, okay, but you are collecting more of A than of B, right, because you're closer to the boiling point of A. So you will see that the temperature in the thermometer will slowly rise until it reaches 50 degrees Celsius, because that's the boiling point of liquid A, right, and you will be majority collecting the fumes of liquid A. The liquid A, for example, the majority of liquid A is going to pass through, okay, and go to the condenser, okay, and that's where it will condense the liquid, okay, and it will collect it into a conical flask over here on the right side. Some things to take note is that your condenser, okay, has cold water that goes in from the bottom, okay, and comes out at the top over here. And you might think this is a very strange way of setting up your condenser, but actually this is a very common way to set up your condenser, okay, because, right, you actually are setting up like a counter current cooling, okay, where the gases are going one way and then the condensing water, right, is going the other way. So when you have a counter current like this, okay, you actually have more efficient cooling of the gases, okay, and you'll make sure that all the gases are being cooled and condensed, and none of them just go through the condenser and come out into the conical flask still as a gas. Another way you can separate your liquids when they are immiscible, that means they cannot be mixed, right, is to actually use this apparatus called a separating funnel. And a diagram of this is over here, right, and it's actually more kind of like shaped like this, okay, with a tap at the bottom, right, it's very iconic, okay, and how you're going to separate them is just based on the difference in density. Okay, for example, here we can separate oil and water, and all you have to do is you're going to shake the separating funnel with the tap closed, okay, with this mixture, okay, and after you shake, right, you're going to leave the liquids to settle, And afterwards, once it's settled, you're going to see two different layers, okay? For example, for oil and water, oil will be at the top and water will be at the bottom because water is denser than oil. Okay, and after that, you are going to just open the tap and collect the water first. And after you've collected the water, okay, then you're going to swap out the conical flask, and then you put a new conical flask and collect the oil later on. So when your liquids are immiscible, it's actually quite easy to go and separate them using this separatory funnel. Alright, so now that we have covered separating of liquids, okay, an additional method, okay, is to use fractional distillation. So fractional distillation is a form of simple distillation, okay, except that you mainly use this, right, when you have a mixture of liquids that are miscible, okay, and maybe if they are closer in boiling point. The only difference between fractional distillation and simple distillation is that fractional distillation uses a fractionating column. So the purpose of this fractionating column is that you basically attach it to the round bottom flask, okay, and it's in between the round bottom flask and the condenser, and it basically provides glass beads, alright, for a larger surface area for your vapor to condense on. So it's not very easy for your low temperature gases, which haven't really reached the boiling point, to reach the condenser, because when they condense on the surface, they're just going to drip back down into the round bottom flask and heat up more. So if you look at this diagram on the right over here, you really see that the fractionating column is just in the middle of the round bottom flask and the condenser, and it's mainly just placed with a lot of glass beads, okay, which provides more surface area, right, for your gas to condense on. And what this helps in is actually helps to further purify, okay, the liquid collected. Remember, in simple distillation, it's actually very difficult to control the gases that evaporate, okay, below their boiling points and condense later on, right? But with a fractionating column, you can control this slightly better, okay, and therefore your gases that haven't really reached their boiling point, they will not really condense into the conical flask. Instead, they will condense on the fractionating column, and they will not reach the conical flask because of this. So what are some of my industrial applications of fractional distillation? Well, one, okay, you can actually obtain nitrogen, argon, and oxygen because they have different boiling points in liquid air, right? So you actually have it at very low temperatures, but you can still separate them out. You can also separate petroleum, okay, into useful fractions, and you actually come to learn this in your fuels chapter, okay, in secondary 4, where your petroleum or your crude oil can be separated into many different fractions, okay. For example, you can separate it into bitumen, you can separate it into naphthalene, you can separate it even into your petrol, right, that you use in your cars. You can also obtain ethanol, okay, that's produced by the fermentation of your glucose solution. Okay, this is actually a industrial way to produce your ethanol, and you actually learn more of this in your alcohols chapter, right, in secondary 4 as well. One of the most simple separation techniques is actually chromatography, and is actually commonly tested in your exams as well. Chromatography is actually a way to separate two or more components that dissolve in the same solvent. So what it actually separates the components with is through the difference in solubility. So a typical setup for your chromatography would be as such, where you put it into a container, or you could actually just use a beaker, okay, with the solvent first, alright, and you have this chromatography paper which you set up, okay. Usually you will have a start line, okay, which is over here, and this start line will have the various spots, okay, at the start line, and as the solvent runs upwards, because your chromatography paper is going to absorb the solvent, okay, the different substances, okay, in the original spots on the start line are going to run up with the solvent, and the more soluble you are, for example this yellow dot over here, the more soluble the spot or the substance, the further it travels in the chromatography paper. Which makes sense because as the solvent travels upwards, if you're more soluble, you'll just travel further with the solvent itself. Okay, so they are actually going to separate based on their solubilities. Now, a common question that is asked is, why is the start line, okay, not drawn in pen? Okay, you want to draw this in pencil, okay, because the ink, okay, will interfere with the results. Okay, because the ink could be soluble inside the solvent. Okay, because it could be soluble in the solvent. Right? And usually you don't want to also run the solvent all the way up. Okay, you will draw a line for the solvent front, okay, to cut the experiment as well. Another important thing in chromatography is the RF value as well. So usually questions will ask you to calculate the RF value. The formula is very simple. It's just the distance traveled by the spot divided by the distance traveled by the solvent. So if you were to look at this example over here, okay, the distance traveled by, let's say, this red spot over here, right? This would be the distance traveled from the start line to where the red spot is. Okay, sometimes you use a ruler to go and measure it, and then you will divide this by the distance traveled by the solvent. Again, it must start from the start line all the way to the solvent front, and that is how you calculate your RF value. Now, if your RF value of the spot is very similar, okay, to the RF value of another spot, for example over here, this typically means that it has the same component inside the mixture itself. So in this case, we'll say that mixture A and B both have the same components of the red spot, the pink spot together. Lastly, in chromatography, you need to know about locating agents as well. So locating agents are very useful in locating or spotting your colorless substances. For example, ninhydrin, right, it's a very common locating agent used to spot amino acids. We're about to wrap this up, so we are going to end this with determining purity. Now, determining purity is very important because, as you know, impurities, right, in drugs and medicines have very undesirable side effects, and well, in general, you just don't really want anything too impure, right? Doesn't it worry you if you ingest something impure or eat something impure, right? So yeah, purity is pretty important. And your production of your silicon chips, for example, and it's not only relevant to things that you eat only, right? It's also relevant to things that you use. For example, your silicon chips, right, in your electronics, okay, a small amount of impurities will actually affect its efficiency as well. So you want to watch out for the purity of chemical substances. And how we do this, okay, in general, okay, for a pure solid, right, it will have a sharp and constant melting point if it's pure, right? If it has impurities, right, the impurities will actually lower the melting point, and if you have more impurities, it will lower the melting point more. So what will happen is that when you try to melt something that's impure, right, you will melt it over a range of temperatures, which is not very ideal, obviously. Okay, if it's a liquid, same concept, okay, we'll have a very sharp and constant boiling point if it was pure. If it was impure, okay, it will actually be the opposite. The impurities will not lower but actually increase the boiling point. Okay, and if it has impurities, it will obviously boil over a range of temperatures as well. If you enjoyed today's video, be sure to hit the subscribe button so that you don't miss out on free content like this to continue improving your chemistry. If you want to join our chemistry online classes, be sure to hit the link below so that you can book a free trial class with us as well. I'll see you all in the next video.